Strike launch. Engagement plan 35 received. Request execute. Plan 35 at launch time earliest.
Launch strike. Jet batteries released. Execute plan 35.
In command and control warfare, missions such as signal exploitation and communications planning increasingly demand a detailed understanding of the behavior of electromagnetic waves.
The behavior of radio waves in free space is fairly well understood. However, the propagation of a wave through space becomes much more complicated in terrestrial applications. Some of the complicating factors include topography, weather, ionospheric conditions, and ambient radio noise. These factors can create special cases, which are often not obvious and sometimes counterintuitive.
At the University of Texas Applied Research Laboratories, the Radio Frequency Mission Planner project is creating a system to exploit those special cases and improve a wide variety of missions. That system is rfmp, the Radio Frequency Mission Planner.
Taking advantage of these special cases can improve a variety of missions, including signal acquisition, evasion, geolocation, jamming, deconfliction, and general communication systems planning. Incorporating these special cases into mission planning requires improved methods for both visualizing and modeling the RF environment. These methods must provide the flexibility, automation, and integration necessary for thorough, accurate, and timely planning.
To this end, rfmp is a synthesis of several powerful propagation models used to determine such factors as propagation loss, field strength, signal strength, probability of detection, probability of acquisition, and propagation mode. These capabilities are enhanced by an intuitive user interface, creating a powerful tool for mission planning.
I'm using the Radio Frequency Mission Planner to determine reasonable location for a ground-based transmitter and a ship-based receiver, looking for locations for good comms, but where also the signal emitted by the ground-based transmitter would be shielded by terrain to avoid detection of that signal by other than friendly units.
After David executes an analysis for signal strength, rfmp produces a color-coded display. In this case, green represents areas of high signal strength, while the signal becomes progressively weaker in the blue, yellow, orange, and red areas. The results are a two-dimensional slice of the 3D analysis volume. This slice is projected onto the terrain map and may be moved to various altitudes, with the changing colors reflecting the variations in signal strength. The altitude can be referenced to either mean sea level, as in this case where the slice is broken by the terrain at lower elevations, or it can be switched to a ground level reference, which produces a display where the data conforms to the terrain. This conformal slice is ideal for the analysis of land-based transceivers. With a slice 10 meters above ground, the results show that the terrain shields the signal from landward detection, while providing several channels of high signal strength for the ship at sea. To further explore the effects of terrain, David uses the profile function to observe signal strength along a vertical plane in the analysis volume. The profile can also be seen in the three-dimensional display for a more comprehensive understanding of the area's topography. In addition to which, David can use the three-dimensional display to observe both mean sea level and conformal slices. He can manipulate RFMP's virtual camera to navigate the entire volume and chart the significant features of the electromagnetic landscape. It enables him to find a tactically superior position that still meets communications needs. In order to further examine specific locations, David can use the lot plot. The lot plot provides a visualization of the joint noise and signal probability density function for the receiver at any selected location within the analysis volume. Although mainly used for technical analysis, it does provide the probability of successful reception at a specific location, and can be used to test sites suggested by the other displays. Employing the Radio Frequency Mission Planner's full complement of displays, David has quickly extracted the information he needs to build a better mission. but this session demonstrates only a fraction of RFMP's potential. The format he used for exploring different aspects of signal strength can be used for the results of other analysis functions, such as probability of signal acquisition or field strength. It can also be used to study individual propagation modes, such as line of sight, which is especially useful for UHF missions. This flexibility is one of the distinct advantages of RFMP's standardized user interface. Multiple analysis functions can be run on a given scenario with little, if any, modification. Because RFMP uses an application programmer's interface to integrate various propagation models. This level of flexibility and automation redefines the possibilities for mission planning. As useful as RFMP is now, the designers are already working on improvements. This already powerful tool will be enhanced in the future versions by making the models account for noise, changing weather, ionospheric factors, variance over time, as well as multiple emitters and receivers. By expanding the variables, the designers are augmenting RFMP's prodigious capabilities and providing the means to build smarter missions. RFMP is the wave of the future. It transforms the complexities of electromagnetic radiation into opportunities, and in today's world, the ability to find and exploit those opportunities can be the key to success.